All right, now let's see where we're at now. We've made some nice little substitutions here. So we've taken our f prime, we know that's v divided by lambda prime, and then replaced lambda with this nice little equation that we developed here. Now this thing looks a bit complicated, but if we look through, we can actually factor out a few things. Notice there's a lambda in this section of the equation, and there's another one in this section of the equation as well. So let's factor out a lambda. So we have lambda times 1 is going to give us lambda. Lambda times Vs over V is going to give us back to our original Vs lambda divided by V. So we've cleaned it up a little bit, and we look at this. It looks like a nice cleaned up version of it. All right, now another thing to consider is this. If we look here, we've got V divided by lambda itself. The original velocity divided by the original wavelength. Hey, isn't that the frequency? The original frequency when we actually started out with this entire problem. So let's take a look over here. Can I replace this, V divided by lambda, with the frequency itself? And that leaves us this nice little term that we have here. All right, now, let's take a look and see how we can utilize this formula. So let's make up a frequency. When I went to the store and I purchased the siren or the ambulance siren, I purchased one that said 1,000 hertz right on the box. That's the sound that you'll produce if you're not moving. And that's the one that says right on the box for the ambulance. Okay? Now, if we take 1,000 hertz, let's multiply by 1. And then in the bottom, we have 1 minus these other factors. Now, Vs, this is very important. That's the velocity of the source of the sound. That's the velocity of the police car or ambulance. It's how fast it's moving. That is not the velocity of sound. So the S down below means the source of the sound. The thing that's making the sound, it's the thing that's moving. So I'm going to make up a number. Let's say the police car is moving at 50 meters per second. V, plain old V, that's the velocity of sound. So when I see just a plain V, I'm going to write down 343 meters per second, as long as they don't give me the temperature. So when we put these numbers in the calculator, we end up with 1 divided by 1 minus, this is about 0.85 on the bottom when we're done. 1 divided by 0.85 is a factor of about 1.17. So we multiply this through. Our final frequency that we actually hear is going to be around 1170 hertz. So if we listen to the pitch, we start out with at 1,000 hertz. Now, as we come running along, moving fast, the person down there is going to hear and the pitch actually goes up, and we're going to hear a slightly higher elevated pitch sound. And we know this because we've heard this with ambulances and police cars all our life. So it's not just the loudness that changes, it's also the pitch, the sound, the frequency of it. Well, remember where this all came from. As we climbed up on the back of the previous wave, we shortened the wavelength. As a consequence, if the wavelength goes down, the pitch, the frequency has to go up. So it goes higher, and we end up with a sound that has an increase in the pitch. This is known as the Doppler effect. Now, this formula is good for a source of sound that is approaching a stationary observer. So, what does it mean? It means that the source of the sound is the thing that's moving. It's approaching somebody who's standing there. So, for example, you're at the scene of an accident, you can hear the police cars coming towards you in the distance, and there you are standing there, you're going to hear 11,070 hertz. All right, now, is it possible that the police car ambulance misses the scene and then drives on by? So if we look there, as a consequence, all right, instead of climbing up on the back of the wave, as you run away from the wave, isn't going to end up increasing the wavelength. So here, the final wavelength is going to be the distance that you started originally, and instead of subtracting it because you're coming towards it, you're actually going farther away, stretching the wave out. This will change to a plus sign. So if we look at our formula, we can change this and just put a plus sign here, and then this is for a situation where the source of sound that is receding is receding from a stationary observer. All right, what does that mean? It means the ambulance has passed by, and then you start to hear a different pitch. All right, now, by changing that to a plus sign, this factor becomes less than 1, and we're going to end up with a hertz less than 1,000. Let me guess, 900 hertz. So the pitch is going to sound a little bit low. So let's recap. As the thing approaches, the pitch goes higher, 1170. Now, when they recede, the wave stretches out. We end up with so approach, recede, and we've got ourselves some nice formulas for calculating these at this time.